Hello everyone from Math 1340, Statistics. It's Professor Wenson here again with a video on your KnewtonAlta homework for section 4.1 titled The Probability Distribution Function, also known as the Probability Density Function, as you're going to see in the instruction, aka a PDF, right? Probability Density Function, Probability Distribution Function, PDF, for a discrete random variable. Alright, so I'm going right into the assignment. Again, mine's a preview. You're going to see the actual thing. Typical KnewtonAlta homework assignment. You've seen it plenty by now. Mastery bar up here. The current objective that this question is on. Now, there is only one objective in this section. It's a very short introduction. Should be a short assignment. And it's understand the properties of a discrete probability, density function. Again, I said probability. In your OpenStax book, it's called a probability distribution function. In this KnewtonAlta instruction, it's called a probability density function. And personally, I've seen probability density function more often in other textbooks. But for short, PDF. Alright, so the first time I'm seeing this objective, let's take a look at more instruction. Right. So we're introduced to things called random variables. Now you've heard of variables before. A random variable is a variable that is subject to change due to chance and events. It describes the outcomes of a statistical experiment, and it can take on a set of different possible values. Each random variable value can vary with each repetition of an experiment, and each one has an associated probability, right, in contrast to other mathematical variables. Right? So we're going to have a random variable, which is going to be describing like all possible outcomes of an experiment. Right? The different values of the variable is the possible outcomes of the experiment, and then next to that, we're going to state what's the probability of getting that particular value. And we'll make a little chart. You'll see we've seen probability charts before. This is the same thing pretty much, just with a discrete variable. And if you recall the difference between discrete and continuous variables back in chapter 1, discrete data versus continuous data. Discrete data was, data that could be counted. 1, 2, 3, 4, 5, etc. Data that had a finite number of values or an infinite number of values, but that could be counted. Continuous, on the other hand, were values that had to be measured, like weight, height, temperature, stuff like that. Notation for a random variable is an uppercase letter, usually a capital X or a capital Y. Again, it could be any letter. These variables are usually represented with words and do not have numerical values, i.e., for example, the random variable X represents the number of blue cars on the highway. And this would be an example of a discrete random variable, right? Because you can count the number of blue cars, right? There are 0 or 1 or 2 or 3, etc. Lowercase letters like little x or little y denote the value of a random variable, and little x is given as a numerical value of the random variable. All right, so for example, the experiment here is, you are flipping 3 fair coins, and you want to know the possible outcomes. So a variable associated with this experiment could be the following. This is just one example. Say the random variable capital X represents the number of heads you get when you perform this experiment, when you toss the 3 fair coins. Now the sample space, remember sample space is the list of all possible outcomes. You have 3 tails up to 3 heads. There are 8 possible outcomes. But for this particular random variable, see how capital X was the number of heads you could get? Well, you can get 0 heads, just 1 head in the 3 flips, exactly 2 heads in the 3 flips, or all 3. So the the different possible values of this variable x are represented by little x, could be 0, 1, 2, or 3. Again, because when you toss 3 coins, you have the possibility of getting 0 heads, 1 head, 2 heads, or 3 heads. Right. Now, capital X represents a variable in words, and the lowercase x has possible outcome numerical values attached to it. For this example, the lowercase x values are countable outcomes. Right? You can count the number of heads when you flip 3 coins, or flip a coin 3 times. So again, going back to the first chapter, and I mentioned this earlier a few minutes ago, recall that discrete data are data that you can count as opposed to data that you have to measure. Right? Measuring data was continuous data. So, because you can count the possible values that the random variable x can have, and the outcomes are random, capital X would be called a discrete random variable. All right, so this random variable x, the number of heads you get when you toss 3 fair coins, that's considered a discrete random variable because the possible outcomes are countable. Right, you can count them, count the number of heads. All right, so again, some definitions here. Now let's continue on with a question. So, which are properties of a random variable? And select all that apply. Random variables are denoted with a lowercase letter. That is not true. Right? The values, the possible values a random variable can take, are denoted with the lowercase letter. Remember, the variable itself is denoted with an uppercase letter. Random variables are represented by numerical values. No. A random variable will be described in words. The outcomes are represented in numerical values. Right? So not represented by numerical values. And discrete random variables do not have values that are countable. Well, no, they actually do. Right? This discrete means that they are countable. They have values that are countable. Right. Okay. And again, they explain exactly what was explained up top in the instruction. Right. Right. Now, we're going to be making little charts or looking at charts where down one column you have all the possible values of a random variable, in this case a discrete random variable, and down the other column you have the probability that the random variable takes that value. So we summarize and then this chart here, this description of all possible outputs, all possible values of the random variable and their probabilities is called a probability density function, right? You have an input output like a function, right? Input x, output probability of that x. Right? And as mentioned before, this is also known as the probability distribution function, but they're using the word density here. So we summarize the probability that a discrete random variable capital X takes on certain values of little x by way of a discrete probability density function. A discrete probability density function describes the relative likelihood or probability for a discrete random variable to take on a given value. The probability density function is usually shown in a table with one column labeled little x or little y. It depends on how you label the random variable, showing the specific values that the random variable capital X can have. And one column labeled the probability that capital X equals little x. What's the probability that the random variable takes on those specific values. So for example, let's look at the table below, which shows the probabilities of the number of heads you would flip if you flipped 3 fair coins. So this is going back to the exact same example up here, flipping a coin 3 times or flipping 3 coins, having random variable capital X be the number of heads you get. Right? So little x can be 0, 1, 2, or 3. And then, looking at the sample space here, all these equally likely outcomes when you flip a coin 3 times, the probability of flipping 0 heads is, all tails, and that's 1 out of the 8. The probability of flipping exactly 1 head, that's these 3 outcomes out of the 8, so 3 out of 8. The probability of flipping exactly 2 heads is, these 3 outcomes, which is 3 out of the 8. And the probability of getting all 3 heads is this 1 outcome out of the 8. So you're seeing this table down here. As I mentioned, 0 heads, probability 1 out of 8. 1 head, probability 3 out of 8. 3/8. 2 heads, 3/8. 3 out of 8. And all 3 being heads, 1 out of 8. All right. And this is called, the probability density function for that discrete random variable. All right, so notice the random variable capital X is, the number of heads showing after 3 fair coins are flipped. The left column with the little x shows the number of possible outcomes, 0, 1, 2, or 3. And the right column shows the probability that capital X takes on each of those values out of the possible 8 outcomes. All right. So there are 2 other important characteristics to note about probability density functions, and these are actually some characteristics we've already pointed out in previous chapters or in previous sections when it comes to probability, or even a relative frequency table. Each probability is between 0 and 1 inclusive, meaning it can be 0 up to 1, it can be 1. But you're not going to have a probability greater than 1 or greater than 100%, and you're not going to have any negative probabilities. All right, so that's happening here in this chart on the top here. All the probabilities are between 0 and 1. Okay. This and 2, again, we've seen this before as well. The sum of all the probabilities is 1. Or 100%, right? This is because all of the possible outcomes are listed in the table. Right? If all possible outcomes, this 0, 1, 2, and 3, heads, is listed, then the sum, right, add up all the probabilities, and you should get 1, or if it's in percentages, right, 100%. Let's check it out. 1/8 plus 3/8 plus 3/8 plus 1/8 would be 8/8, right, as they're shown here, which is equal to 1. If this does not happen, then you do not have a proper probability density function. Right? So all the probabilities should be from 0 to 1, and the sum of all the probabilities should be equal to 1. Right? All right. So again, here, using the table above, what is the probability that 2 heads appear when 3 fair coins are flipped? So the probability x equals 2, well, I go to the 2 row here, it's 3/8. Hopefully this is pretty easy to read. All right, so again, some more key terms. Already read through some definitions there. Let's continue on with the question. All right, now the table below shows a probability density function for a discrete random variable called capital X. What is the probability that capital X takes on the value of 2? Well, gee, 1/12. Right? I go to little x equals 2, and what's the probability that capital X takes on the value of 2? It's 1/12. Very hopefully very easy to read. Wonderful. All right. So now we're out of the instruction, still in the same objective here. Looks like I'm halfway done. All right, so now the question is, which of the following tables shows a valid probability density function? So remember, all the probabilities need to be from 0 to 1, and the sum of the probabilities must be equal to 1. All right, so first one, you're given your possible values of the random variable x over here. All these probabilities are from 0 to 1. So far, so good. Now let's add them up. Now I'll get a common denominator, which would be 8. 1/4 is 2/8. So you have 2/8 plus 3/8 would be 5/8 plus 3/8 again would be 8/8. That's 1. So all the probabilities are from 0 to 1, and the sum of the probabilities is equal to 1. this is a valid probability density function. How about this? Again, the possible values of x over here, and then their probabilities. Now, all the probabilities are from 0 to 1. So far, so good. And then add them up. 1/8 plus 1/8 plus 3/4 is 6/8. You get a common denominator. So 1/8 plus 1/8 is 2/8 plus 6/8 would be 8/8, which is again 1. This is also a valid probability density function. All right, here, possible values of x listed, their probabilities, and couple things wrong. One, negative probability. The probability that x equals 0 is negative. That will never happen. So this is not a valid probability density function. Okay. Even though if you add these up, you get 1, right? Because negative 3/10 plus 1/10 is negative 2/10, which is negative 1/5 plus 1/5 is 0 plus 1 is 1. Yeah, the sum of the probabilities is 1, but one of the not all of the probabilities are from 0 to 1. One of them is below 0, it's negative. So I'm not picking that one. Here, list of the possible outcomes, possible values of x, capital X, and probabilities. All the probabilities are from 0 to 1, right? They're from 0 to 1, so that's good. But look at the sum. Add them all up. 0.74 plus 0.0 would just be 0.74, but then plus 0.54 would be 1.28, which is bigger than 1, not equal to 1. So this is, again, not a valid probability density function. Here, possible outcomes, probabilities. All the probabilities are from 0 to 1. Add them up. 1/10 plus 2/10, right? 1/5 is 2/10, that's 3/10 plus 6/10. Well, 1/10 plus 2/10 is 3/10 plus 6/10 is 9/10. Or you can go 0.1 plus 0.2 is 0.3 plus 0.6 is 0.9. They add up to 0.9, 9/10, not 1. So this is not a valid probability density function. And then lastly, all the outcomes listed, probabilities listed. All the probabilities are from 0 to 1. Great. And look at their sum. 0.18 plus 0.76 is 0.94 plus 0.06 would be 1 exactly. So that's a valid probability density function. Great. All right. So now, careful here. Look at this. Careful. Table shows a probability density function, right, for a discrete random variable x. What is the probability that x is 2 or 3? Remember, when you have the probability of event A or event B, that'll involve addition. That OR rule, that addition rule, you learned in chapter 3. Now, according to this chart here, x can't be 2 and 3 at the same time. So these are mutually exclusive events, right? X being equal to 2 and x being equal to 3 are mutually exclusive or disjoint events. Remember, they can't happen at the same time. So when I want the probability that x is 2 or x is 3, I'm just adding those up. What's the probability that x is 2 plus the probability that x is 3? So the probability that x is 2 is 1/16 plus the probability that x is 3 is 1/4, which is 4/16, right? Getting a common denominator. And then adding these two together, 1/16 plus 4/16 is 5/16. Right? So just simply enter 5/16 like that. All right, because notice they didn't say round. Oh yeah, it says provide the final answer as a fraction. So I've already done that. All right. Come on. There we go. And again, the explanation. So again, be careful. Right? One of the times I looked at it, it was just what if x was 2, but this is adding more to it, or x equals 2 or 3. All right, and that looks like about it. You'll have problems similar to that. So again, your one focus is on can you read one of these charts to find probabilities? Can you read one of these probability density functions or PDFs? And another one are, do you know a couple properties? What should be happening in a valid probability density function? So remember, all the probabilities are going to be from 0 to 1. Nothing bigger than 1, nothing less than 0. And then the sum of all the probabilities, right, for all the possible outcomes must be equal to 1 or 100%. And that's really about it for this. Right? So hopefully this video is a good guide for you when you go through this Section 4.1 homework on your own. And of course, let me know if you have any questions, and thank you very much for watching.